Okay, good evening, Ms. Durike and Mr. Jody. Today, our group will present our research poster entitled Segmentation of Liver and Tumor Regions in CT scan images using UNET. This study focuses on the application of deep learning for automatic liver and tumor segmentation in CT scan images. We compared the performance of three architectures, Simple CNN, Simple SegNet, and UNET, using the LITS dataset to identify the most effective model for this task. In this presentation, we will briefly discuss the background of the study, the methodology, the experimental results, and the conclusion drawn from our research. Without further ado, let's begin with the introduction. For the introduction, liver cancer is one of the deadliest cancers worldwide. Accurate identification of liver and tumor boundaries in CT scans is essential for diagnosis, treatment planning, and surgical decision making. However, manual segmentation is time-consuming and can vary between clinicians. Therefore, automated segmentation using deep learning has become increasingly important. For the related literature, previous studies have explored advanced architectures such as 3D UNET, Attention UNET, and UNET++. However, many studies lack standardized preprocessing and reproducible evaluation methods. This study aims to establish a transparent and reproducible baseline using UNET. For the objective, this study aims to compare the performance of Simple CNN, Simple SegNet, and UNET for liver and tumor segmentation on the LITS dataset. It also investigates the effectiveness of dice BCE loss in handling class imbalance and establishing a reliable baseline for future research. The research question is, can a standard UNET with proper preprocessing outperform Simple CNN-based architectures for medical image segmentation? Next is methodology.
The study used the LITS dataset containing abdominal CT scans. A total of 6,802 informative axial slices were extracted from 51 CT volumes. The preprocessing pipeline includes HU windowing, mass binarization, normalization, and resize image to 128 and 128 pixels. The dataset was split into 18% training and 20% validation data. Three models, Simple CNN, Simple SegNet, and UNET, were trained for 30 epochs using the Adam optimizer and dice BCE loss on an NVIDIA Tesla T4 GPU. The next is result or findings. The result show that UNET significantly outperformed the other two models. UNET achieved a dice score of 98% and an IOU of 97%, while Simple CNN and Simple SegNet only achieved dice score around 71% and 72%. Visual evaluation also demonstrates that UNET accurately segmented both liver regions and small tumor lesions across different CT scan appears. Okay, the next is analysis.
Okay, for the analysis, the main reason behind UNET's superior performance is it skips connections. Simple CNN lacks an encoder-decoder structure and struggles to capture spatial context. Simple SegNet includes an encoder-decoder architecture but loses important spatial information during downsampling. UNET preserves spatial details through skip connections, resulting in more accurate segmentation boundaries and substantially higher performance metrics. So compared with previous studies, our proposed UNET achieved an accuracy of 99.92%, outperforming light CNN with 95.6 accuracy and cool ELM with 96% accuracy. And the next is conclusion. The study demonstrates that UNET is highly effective for automatic liver and tumor segmentation in CT images. By combining a carefully designed preprocessing pipeline with dice BCE loss, the model achieved a dice score of 0.986 and an accuracy of 99.82%, outperforming both baseline models and several previous approaches. These findings highlight the importance of skip connections in preserving spatial information and improving medical image segmentation performance. That concludes our presentation. Thank you for listening.